Okay, so linearization at equilibrium. This will be a little bit of a long video of these because there's a lot of calculations. So linearization, you've seen linearization back in calculus 1. If you remember, how do you estimate square root of 120? Well, you look at the graph of y equals square root of x. What you want to know is if x is 120, what's square root of 120? And what we can do is we can go up to, say, 121 and build the tangent line, which I'm going to try and draw here, but it'll be a little bit tricky. There's my tangent line. Remember that the formula for a tangent line is L of x equals the function at a plus f prime of a times x minus a, right? So f of a, that's the point at which you are, f prime of a is the slope. So the tangent line here, well, the square root of 121 is 11 plus 1 over 22, that's the derivative of y equals square root of x at x equals 121 times x minus 121. And what we're interested in is when x is 120, what do we get? It's 120 minus 121. So the tangent line gives us 11 minus 1 over 22. And that should be a good approximation to the square root of 120. So we use the tangent line to estimate the value of the function near a point where you can actually calculate what the derivative is. And this is linearization. The closer this point is, 120 is to 121, the better the approximation. If we wanted the square root of 110 instead of 120, the approximation would be not quite so good. If we wanted the square root of 120.5, the approximation would be better. So if we're close to the point of linearization, the tangent line gives you a good approximation. And the closer you get, the better the approximation. Now we can do this at Equilibria. So we can approximate our components using Taylor's theorems for functions of multiple variables at a point x is 0, y 0. So our function, our vector field, is this. And our differential equation is that. So we want to be able to use linearization to approximate the vector field, and then that tells us we can try and approximate the solution curves. So our components, oh, I need to make another note up here. Oh, we already have a point x0, y0. So f of x and y, same kind of thing. It's f of x0, y0 plus, now the first derivative with respect to x at the point x0, y0 times x minus x0. This looks a lot like our formula for linearization in one dimension, f of a plus f prime of a, x minus a. But now we also need another term to reflect the y component. And hot stands for higher order terms. So Taylor's theorem, right? You get an x squared term, x cubed term, etc. Likewise, g of xy is the same thing. It's g x0, y0 plus the derivative with respect to x evaluated at a point times x minus x0 plus the derivative with respect to y at a point y minus y0 plus higher order terms. Well, I'm not going to actually try and write that out because the notation get messy, but the higher order terms go to 0 as your point xy goes to x0. So these go to 0, and they go to 0 faster than this, right? They're basically squared terms, cubic terms, etc. So there's our approximation. We're generally going to just truncate the approximation here and ignore the higher order terms. That's going to turn all these into closely equal to. Now, when x0, y0 is in equilibrium, well, that means that the components themselves are actually equal to 0 at those points. Their derivatives might not be, but the components are. So that tells me then that if we look at these two equations, f of xy is roughly equal to the derivative times x minus x0 plus the derivative with respect to y times y minus y0, and then g sub x, x0, y0, x minus x0 plus g sub y, x0, y0 times y minus y0. Okay, so we can rewrite this then as in matrix form. This left-hand side is our vector function, v of xy, f of xy. Oops, let me undo that real quick. So that's the function f of x, y. Those are the two components. And now those are roughly equal to this whole thing here. But I can rewrite that as a matrix of partial derivatives evaluated at the point x0, y0. So this matrix here that I'm writing down, that's a matrix of numbers because we're taking functions and evaluating them at a specific point, and then times x minus x0, y minus y0. So that's a rough approximation of our function. So if we're looking at the equation that we want to solve, which is y prime of t equals f of x comma y, right? That's the equation x prime of t, y prime of t equals f of xy, g of xy. Now, the problem is, of course, is that this is in terms of x's, this is in terms of x minus x naught, but we can note that the derivative of x of t minus x0 is, in fact, just the derivative of x prime of t. And likewise, the derivative of y of t minus y0 is just y prime of t. So what does that mean? I can change to local coordinates what that means is I'm trying to put the equilibrium at 0, 0. Local coordinates. We'll set u equal to x minus x0, y, no, v equals y minus y0. And as we note above, right, here and here, that means that u prime of t equals x prime of t, and that v prime of t equals y prime of t. And so finally, what that means is that this equation, becomes u prime of t, v prime of t equals, roughly, this whole thing. So fx at x0, y0, fy at x0, y0, dx at x0, y0, gy at x0, y0. And then this is u, and this is v. Remember that this matrix is just all numbers. So now we're just back in the world of 327, where you have a matrix of numbers, and you need to find the eigenvalues and the eigenvectors to figure out the solutions. This matrix is, as you saw in vector calculus, the Jacobian of the function f evaluated at the point x0, y0. And so that's our little batch of theory there. My comment. Oh, here's my comment. So the conclusion to all this, we'll just move this up a tad. So the conclusion to all this is near an equilibrium x0, y0, the system behaves like the linearized system with matrix Jacobian of f at x0, y0, except we have to be a little bit careful. If the real part of the eigenvalues is 0, then there's a little problem with the analysis. But that tells us what happens near an equilibrium. We just have to figure out what happens for this particular system. So how does this work out for example? So we'll start at the equilibrium 0, 0. Oh, we'll start by figuring out what the Jacobian is. So the Jacobian of a function, of the function that we're using, right, is fx, fy, gx, gy. Note that each row is the gradient of a component. This is the gradient of the x component. This is the gradient of the y component. In our particular case, this becomes 10 minus 5y minus 5x. If you go back and check your notes, y and 3 plus x minus 6y. So at the equilibrium 0, 0, what do we have for the Jacobian of f at the point 0, 0? Well, you just plug in 0 for x and 0 for y, and you get 10, 0, 0, 3. Right? What's our eigenvalues and our eigenvectors? You can go and look this up on an online eigenvalue, eigenvector calculator. I would suggest doing that instead of doing all this by hand. But we have lambda 1 equals 10 with eigenvector v1 being 1, 0, and eigenvector lambda 2 equals 3 with v2 being 0, 1. So we can draw a little picture. What happens near the equilibrium 0, 0 is we have 1, 0, which is the x-axis, as one eigendirection, and you're going out because lambda is positive, and you have the y-axis as the other eigendirection, and lambda 2 is positive, so you're going out. Lambda 2 is the smaller of the two eigenvalues, the one that's closer to 0, so other solutions go out, but they're tangent to the y-axis as they leave the equilibrium. So there's what's going on at the equilibrium 0, 0. We'll just do this similar thing for the other ones. At the equilibrium 0, 1, our Jacobian of f at 0, 1, you can go back up and see what the Jacobian is and plug in the numbers, but it should be plus 5, 0, 1 minus 3. Right? This is a matrix. Plug it into your eigenvalue or eigenvector calculator, and you get that lambda 1 is 5, with eigenvector v1 being 8, 1. And lambda 2 is, there it is, minus 3. And the vector is 0, 1. So what's going on at the point 0, 1 at that equilibrium? Well, the y-axis is 1 eigendirection, and that corresponds to a negative eigenvalue. And the line 8, 1, so that's 8 would be out here and 1. So we have a line that's got a very low slope like that, but you're going out because that's lambda equals plus 5. So that's what it looks like. And this is a saddle. Other solutions look like that. So there's a saddle. And at the other equilibrium, which is x equals 3, y equals 2, the Jacobian of f at 3, 2 is equal to 0 minus 15, 2 minus 6. And the eigenvalues are complex here, minus 3 plus minus I square root of 21. So what does that mean? Well, at the point 3, 2, we have a spiral because it's a complex, and it's a sink because the real part is negative. So either we're spiraling in like that, or we're spiraling in like that, and we don't know what the direction is. We have to know more about the vector field. So putting that all together, we're beginning to construct a sketch of our vector field. So we'll draw a big XY plane here. Y-axis pretty low. So there's 0, 0, that's one equilibrium. 0, 1 is another equilibrium. I'm not going to label them until I've drawn my picture because I don't know exactly how big my pictures are going to be. And then there's 3, 2. So there's my 3 equilibrium. We know near this point, going out in that direction, out in that direction, and solution curves, other solution curves look like that. So just near the point 0, 0, it'll look like that. The closer you get to 0, 0, the better the approximation. The further away you get, the worse it gets. Now here we have the y-axis, again, is an eigen solution with things going in. And then we have a very shallow line. Where was that picture? There we go. Like this, going out. And so we have a saddle going on at this point. And out here we have a spiral. I'm going to draw it like this, but I don't really know which way the arrows are going. And this is my equilibrium 0, 0 here. This is the equilibrium 0, 1. And this is the equilibrium 3, 2. So we need to sort of fill in the picture a little bit about what's going on in the rest of the plane. And that is what null lines will help us to do. And then once we have that, we'll be able to fill in the rest of the planes and be able to say some statements about what the solution curves are doing.